For centuries, sailors told the same story. A wave would appear from nowhere, a wall of water far taller than anything around it, rising suddenly out of a calm or moderately rough sea with no warning and no apparent cause. It would smash into a ship, sometimes destroying it completely, and then vanish just as quickly as it had appeared. For just as many centuries, scientists did not believe a word of it. This is the story of how an entire category of natural phenomenon was dismissed as superstition for hundreds of years, until the ocean itself produced undeniable proof. And it is the story of what science now understands, and still does not understand, about the most terrifying waves on Earth. Let us start with why scientists refused to believe sailors for so long, because the skepticism was not unreasonable given the tools available at the time. For most of recorded maritime history, the only evidence of an extreme wave was a survivor's account, told after the fact, often in the chaos and trauma of having nearly died. Explorers like Ernest Shackleton, whose Antarctic expeditions placed him in some of the most violent seas on the planet, and Dumont d'Urville, the French explorer who documented enormous waves during his own oceanic voyages, both reported encountering waves that defied the scientific consensus of their era about how large ocean waves could possibly get. But eyewitness testimony, however credible the witness, is not the same as a measurement. Without instruments capable of recording wave height with precision in real time, oceanographers had every reason to treat these accounts as exaggeration, the natural product of fear, darkness, and the disorientation of a violent storm. The mathematical models scientists had built to describe ocean wave behavior reinforced this skepticism. Those models, based on what is called linear wave theory, predicted that waves of the size sailors described should occur so rarely, something like once every 10,000 years, that any individual report of encountering one in a human lifetime seemed statistically implausible. Then came December 12, 1978. In 1978, the MS München is believed to have been hit by a rogue wave and sank. All 28 crew on board were lost. MS München was lost at sea, leaving only scattered wreckage and signs of sudden damage, including extreme forces 20 meters above the waterline. The ship was never found, save for some lifeboats that were hanging 20 meters or 66 feet above the waterline. Given the damage to the lifeboat, it is believed that a wave significantly larger must have hit the ship. 28 people died, and the only physical evidence left behind was a lifeboat damaged in a way that suggested it had been struck by something rising more than 60 feet above the normal waterline. This was the kind of incident that should have forced a scientific reckoning. Instead, in the absence of an instrumental measurement, it remained an open mystery, plausible but unproven. The proof scientists needed finally arrived on New Year's Day, 1995. On 1st January 1995 at 1524 UTC, the most famous freak wave to be detected by a measuring instrument was recorded by a downward-looking laser at the North Sea Dropner gas platform. The wave was 25.6 meters high, with an 18.5 meter crest height. The Dropner platform rig was built to withstand a calculated 1 in 10,000 years wave with a predicted height of 20 meters, and was fitted with state-of-the-art sensors, including a laser rangefinder wave recorder on the platform's underside. The engineers had built their platform to handle the absolute worst case their models could imagine, a wave so rare it should occur only once every 10 millennia. The ocean exceeded that worst-case prediction on its very first attempt to test it. The measured freak wave of 25.6 meters is significantly higher than its surrounding waves. As a general rule, the largest individual wave one may encounter is approximately twice as high as the significant wave height, the average of the highest third of the total waves, which means that waves could not have reached a height of over 24 meters in the Dropner case. The actual measured freak wave could thus not be explained with a significant wave height of almost 12 meters. This is the precise scientific definition that emerged from the Dropner event, and it is worth understanding clearly. Scientists define a rogue wave as any wave more than twice the height of the waves surrounding it. The Dropner wave, for instance, was 25.6 meters tall, while its neighbors were only 12 meters tall. The classification is not about absolute size. A rogue wave can occur in relatively calm seas as easily as in a violent storm, because what defines it is the ratio between that single wave and the surrounding sea state, not its raw height alone. The platform sustained minor damage in the event. In the area, the significant wave height at the time was about 12 meters, so the Dropner wave was more than twice that. The Dropner wave became the first scientifically incontrovertible proof that the centuries of sailors' tales had been describing something real all along. Since then, the recognition of rogue waves has accelerated dramatically, and one event in particular has reshaped scientific thinking about just how extreme these waves can become. On 17th of November 2020, an extreme rogue wave was detected by a buoy maintained by Environment and Climate Change Canada, located off the coast of Ucluelet, British Columbia, in the northeast Pacific Ocean. The 2020 Ucluelet rogue wave was measured at 17.6 meters amid an approximately 6 meter significant wave height, representing a normalized amplification of nearly 3, corresponding to an extremely rare event. Compare this directly to Dropner. The Ucluelet wave was nearly 3 times the size of its peers. The Dropner wave towered over its neighbors at a staggering 85 feet, as the surrounding waves were 39 feet tall. In comparison, the enormous rogue wave recorded off the coast of Vancouver Island, known as the Ucluelet wave, was only 58 feet tall in comparison, but it grew to over 3 times the height of its surrounding waves. This comparison reveals something crucial about how scientists now think about these waves. The Ucluelet wave was, in absolute terms, smaller than the Dropner wave, but relative to the calm sea it emerged from, it was a far more extreme statistical anomaly. Now scientists are trying to understand exactly what makes ocean waves get that big, and how often we can expect them. So, what actually causes a wave to suddenly tower nearly 3 times higher than everything around it? Science currently points to 3 overlapping explanations, and the honest answer is that no single theory fully accounts for every documented case. The first mechanism is constructive interference. Waves from different directions, since waves continue to propagate after the winds that cause them have died away. Thus, lateral wave trains contribute towards constructive interference. Imagine multiple wave systems, generated by different storms in different parts of the ocean, traveling at different speeds and from different directions, eventually crossing paths in the same patch of water. When the peaks of those independent wave systems happen to align at precisely the same moment, their heights add together, briefly producing a single wave dramatically larger than any individual contributing system could create on its own. But constructive interference alone has a problem. However, a linear superposition still does not explain rogue waves. They are higher, deeper, sharper, and more common than they should be. Second-order summations have been attempted, and these do give steeper waves, but do not fully account for them. This gap is exactly why the second mechanism, the interaction between waves and ocean currents, has become a major focus of research, particularly in one specific region of the world. Waves from the southwest are magnified on meeting the Agulhas current. This is well-established physics and is familiar to mariners. These waves meet the strongly flowing Agulhas current. The intersection causes the waves to rise in height, typically by 20 to 40% and up to 60% in extreme situations. These southwest winds and their waves are opposite in direction to the Agulhas current, and strongest where the current is most concentrated. When meeting the current, the waves become shorter in wavelength and steeper. When waves from one direction are driven into an opposing current, this results in shortening of wavelength, causing an increase in wave height and oncoming wave trains to compress together into a rogue wave. Think of it like traffic merging onto a highway that suddenly narrows. The cars do not disappear. They compress together, bunching up because the available space has shrunk while the volume trying to pass through has not. Ocean waves behave similarly when a current pushes directly against their direction of travel. The wave's energy has nowhere to go but upward, and the result is a taller, steeper wave than either the original wind conditions or the current alone could produce. This explains why specific locations on Earth experience rogue waves with far greater frequency than the open ocean generally would predict. With the requirement of strong currents, some parts of the oceans are more prone to this rogue wave generation mechanism than others, such as areas near the Agulhas Current, Gulf Stream, and Kuroshio Current. Research of rogue waves offshore South Africa in the Agulhas Current has shown that wave energy can reflect off the Agulhas Current and focus in areas away from the actual current, producing unexpectedly high waves. This is precisely why the southeastern coast of South Africa has earned a reputation among mariners that long predates any scientific confirmation, an area where ships have reported encountering enormous sudden waves for generations, and where modern science has now confirmed exactly why that reputation is justified. The third explanation moves into genuinely strange territory, borrowed from an entirely different branch of physics. A rogue wave may occur by natural nonlinear processes from a random background of smaller waves. In such a case, it is hypothesized an unusual unstable wave type may form, which sucks energy from other waves, growing to a near vertical monster itself before becoming too unstable and collapsing shortly thereafter. One simple model for this is a wave equation known as the nonlinear Schrödinger equation, in which a normal and perfectly accountable wave begins to soak energy from the waves immediately fore and aft, reducing them to minor ripples compared to other waves. This equation was not originally developed to describe ocean waves at all. Such rogue waves have also been observed in nonlinear optical fibers. The same mathematics that describes how light pulses can suddenly and unpredictably spike in intensity inside fiber optic cables also appears to describe how a patch of ocean can suddenly concentrate the energy of its neighboring waves into a single, unstable, towering peak, before that peak collapses back into the surrounding sea within seconds. The honest, comparative scientific assessment here matters. Recent studies analyzing billions of wave measurements by wave buoys demonstrate that rogue wave occurrence rates in the ocean can be explained with linear theory when the finite spectral bandwidth of the wave spectrum is taken into account. However, whether weakly nonlinear dynamics can explain even the largest rogue waves, such as those exceeding 3 times the significant wave height, which would be exceedingly rare in linear theory, is not yet known. This means the most common rogue waves may be explained reasonably well by ordinary wave statistics, while the most extreme outliers, like Euclid, may require the more exotic nonlinear physics to fully account for. Now, let us address the question of danger directly, because understanding the destructive force involved explains why naval engineers take this threat so seriously. A 12-meter wave in the usual linear model would have a breaking force of 6 metric tons per square meter. Scale that force upward toward the dimensions of a true rogue wave, and the pressure involved can reach roughly 100 tons per square meter, an amount of force capable of crushing reinforced steel structures that were never designed to absorb a single sudden impact of that magnitude. This is precisely why modern ship design has evolved so significantly since the Dropner measurement forced engineers to revise their assumptions. Queen Elizabeth II encountered a 29-meter wave in the North Atlantic during Hurricane Luis. The master said it came out of the darkness and looked like the white cliffs of Dover. The ship survived, largely because of robust hull design that modern naval engineering standards now require specifically in response to documented rogue wave encounters. So what is the realistic likelihood of encountering one of these waves? The comparative answer is reassuring for most people, and sobering for those who spend significant time at sea. Rogue waves remain statistically rare events for any specific location at any specific moment. But the regions where ocean currents create the conditions for wave compression, the Agulhas current, the Gulf Stream, the Kuroshio current, see them with measurably greater frequency than the open ocean average, and modern satellite monitoring and oceanographic forecasting are increasingly able to flag conditions where the risk of encountering one rises substantially. What changed between the centuries of dismissed sailors' tales and today's scientific consensus was never the ocean itself. The waves sailors described were always real. What changed was our ability to measure them and our willingness to let the data overturn a model that had simply never been tested against the full, unpredictable power of the open sea.